Welcome back. This is the third video in my series of lectures on classification and regression trees. The first two videos covered classification trees where the dependent variable, the thing you're trying to predict, was a numerical quantity. This lecture is going to cover classification trees where the thing you're trying to predict is a categorical variable. So, for example, maybe I'm trying to predict whether a part is defective or not, or whether a customer clicks or not, or which brand, brand A, B, or C, will the customer choose. So I'm trying to make a prediction of some categorical variable. Well, in order to understand classification trees, let me review what we were doing with regression trees for a minute and introduce a new term, which is purity or impurity. Okay, so what were we doing with regression trees? What we were doing with regression trees was we were trying to minimize the residual sums of squares. I think I need to make this a little bit smaller. All right, and so what is RSS? This would be the sum over some set of of indices of y sub I minus y bar for that node. And we're going to start calling this an impurity measure. All right, so this is a measure of how impure my node is. So just as a very simple example, let's go take a situation like this where maybe I have a split. And on the right-hand side of this split, I have, say, 4 values that all take exactly the same y. So if I were to fit my regression tree, the mean of these points would go right through the points, and my RSS, let's say this is node 2, this is node 1, would be equal to 0. And we would say this is a perfectly pure node, because we explain all the variance there is to explain with that split. Now let's say my left child is there are points all over the place, and so the mean of those points would be about here, and RSS 1 would be big. All right, and we would call this an impure node. All right, so what we're really trying to do with trees in general is we're going to introduce these splits to improve the purity of my fit. Improve the purity of my fit. And what do I mean by that? Make these sums of squares as small as possible. Well, we can't use this residual sums of squares in the case of a classification model. So let's say I have 3 brands. I have Coke, Pepsi, and RC, and I want to predict your brand choice. So how do I compute the sums of squares of Coke, Pepsi, or RC? It doesn't work. So I need some other way of capturing the impurity of my node. And so there's actually a couple ways that people have proposed to capture that impurity. And the two most common impurity functions, if you will, are the Gini index and the entropy. And so the idea would be something like this. Let's say I have a root node. So this is my root. And we'll just carry on with my little example of I have Coke, I have Pepsi, and I have RC. And let's just say I have 30 people who like Coke. I have maybe 40 people who like Pepsi, and then that would be, let's say 30 people who like RC. Then what we would have is P1 is going to be the proportion of people in this node who like Coke. And so that would be 0.3. P2 is going to be the proportion of people who like Pepsi, which would be 0.4. And P3 would be the proportion of people who like RC, which would also be 0.3. So the idea of Gini, so if we wanted to compute the Gini index, of how impure this node would be, we would take this 1 minus the sum over all these values of p squared sub j. All right, so this would be 1 minus 0.3 squared minus 0.4 squared minus 0.3 squared would tell me how impure this node is. Now, the entropy is going to be this. It's going to be negative the sum of p sub j log p sub j. So in this case, it would be minus the sum of 0.3 times the log of 0.3 plus 0.4 times the log of 0.4 plus 0.3 times the log of 0.3. And that would be my entropy measure of how impure that node is. Now, let's say I could introduce a split. And in this split, I had a situation where this left child had Coke equal to 30, and then I have Pepsi equal to 0 and RC equal to 0. In this case, what I would have, let's just go compute the gini for this right child. It would be 1 minus, well, what fraction of people have Coke? It would be, well, 30 over 30 squared. And then what fraction do I have Pepsi? Well, it'd be 0 over, there are 30 total people in that node. And then what fraction have RC? Well, 0 over 30 squared. And so notice what I have here. I have 1 minus 1 minus 0, which is 0. So my Gini coefficient would tell me this is a perfectly pure node. Likewise, if I used entropy, what you would find is that I would have, well, P1 for Coke would be, well, let's just write it out here. Entropy would be negative the sum of 1 times the log of 1. Notice the log of 1 is 0, so this whole term is 0. Then I would have plus, well, 0 times the log of 0. We're going to go to 0 faster than the log goes to 0, and so we're going to call this 0. Likewise, 0 times the log of 0 would be 0, and we would end up with a 0. So whenever we end up with 0% in one, we take 0 times the log of 0, and we call that a 0. Just for illustration purposes, the plot over here shows the situation where I only have two classes. So maybe I only have Coke and Pepsi. And let's say P1 is the probability you choose Coke. So then 1 minus P1 would be the probability that you choose Pepsi. So in that case, I can show both of these functions, and you see something that's, I guess, kind of intuitive, or it makes sense at least, that if 100% of the people in a node have a preference for Coke, then the impurity is 0, meaning that's a perfectly pure node. Likewise, if 0% like Coke, they all like Pepsi, that would be a perfectly pure node. Both of these functions, entropy and Gini, achieve a maximum value where the fraction of people who like Coke is 50%, and therefore the fraction of people who like Pepsi is also 50%, and those would be the most impure nodes that are possible. Okay, so that's how we characterize the impurity of a node for classification tree. Don't worry about Gini versus entropy. What I've noticed is that some software tends to use Gini, some software tends to use entropy, some software lets you choose. Just use whatever the software offers because these functions have pretty similar shapes. Okay, what else? Well, we also need to characterize the change in impurity. So let's say that I have some node and I'm going to split this parent into a left child and a right child. Then I'm going to say P sub L is the fraction of observations that go to the left child, P sub R is the fraction of cases that go to the right child. The change in impurity is simply going to be the impurity of the parent minus the weighted sum of the impurities of the children. So it's very similar to what we were doing with regression trees, but this is slightly more complicated in that I need to worry about the fraction of cases going to each of the two nodes. So let me kind of just help us a little bit. Hopefully this helps us by refreshing our memory what we were doing with regression trees. So regression trees were very greedy, and they sought the split that would cause the greatest reduction in RSS. And so let's just write this as RSS for the parent node. And so I won't give us any subscript for the parent node, minus RSS for the left child, which we'll just call that RSS1 minus RSS2. So the picture would look something like this. I think I need to make this let's expand this so that we can see it. So this would be the picture of what I have. I have a parent node, I have a left child, I have a right child. And so this would be node number 1, this would be node number 2, this is the parent node. So let's say I have n cases here, I have n1 cases here, and I have n2 cases here. So this measure that I had, I'm going to call it a self-weighting measure. It's a self-weighting. And the reason I call it that is that if I have more cases in this node than in this node, I'm just adding up the errors, and this would be this term would get more weight because I have more cases over here versus fewer cases over here. So that made our life very easy. What would happen if we had used a slightly different measure of impurity? Instead of looking at think of this as the residual sums of squares, what if we took the mean squared error? Okay, so the mean squared error would divide by the size of the node, and that's kind of like what I have here. Okay, so this is not a total measure, it's an average measure of how impure the cases are in each of those nodes. So what would I have to do to make this work? Dividing by the number of cases. So let's just say the change in mean squared error would be RSS over n. Okay, now what I'm going to do here is write this as RSS1, and we can think of this as divided by n, but I'm going to multiply by n1 over n1. And then let's do the same thing here, n2 over n, RSS2 over n2. So notice these two things would cross out, and basically I have everything divided by n. But what I have here is my fraction of cases on the left, so let's just call that P1, and what I have here is P2. This is going to be the mean squared error in my node 1. This is going to be the mean squared error of node 2. So the point is, if I want to work with these measures, with the measure of impurity that takes out the number of cases, then I have to weight these two to end up with an equivalent measure. And so maybe that's a complicated way of explaining why I need to introduce these weights, but I hope the connection helps you. Well, all right, that's enough about the theory of this. Let's go look at an example. So how do you fit these things in R? And the answer is we're going to simply make the dependent variable a factor. So whenever the dependent variable is a factor, R will automatically choose to use either gini or entropy. I don't remember which one it is, but it'll use a suitable impurity measure, and it will switch from using the RSS measure to the deviance measure for a binomial. And notice, instead of getting the predicted values for a regression tree, we get two probabilities. So the way to think about this is the defaulting customer data. Remember, we've looked at this in previous lectures. We have a bunch of people who joined a health club, and we want to predict who is going to cancel their membership. And so the interpretation here is about 11.5% of the people in the root node canceled their membership. The remaining 88.5% did not cancel their membership. So this is the probability of cancel. This is the probability of not cancel. So how does this tree work? Well, I dumped in, looks like 5 variables. So we can't use partition.tree in this case to visualize this other than with a dendrogram. So what happens is R is going to go split on by identifying the the split that would cause the greatest reduction in impurity. And so what we find is that we want to split on payment type. All right, so here's how you, by the way, this is how you handle categorical predictors in a tree. It puts 2 of the values for payment type, so checking EFT and credit EFT, on one node, and then it puts the other 2 values on the right-hand side. So on the right-hand side, we have book and statement, and what we see is that, well, there's a very low probability if you use either of these electronic fund transfer methods. There's only a 1.4% chance that you go away. This node, by the maximum likelihood classification method, turns out to be predicted to be 0 because this probability is so small. Okay, well, what does R do next? Well, R is going to try to identify a way to split this left child, and it's going to fail. So it can't find any good splits, and therefore it's not going to continue on that path. We have a terminal node. So notice we had about 25,000 cases, 12,000 cases went left, the remaining 13,000 cases went to the right child. And so then what does it do now? Well, it's going to go search for a split, and it's going to find that the best split is where down payment is less than $123. So what you'll see is that if you put less than $123 and you pay with one of these book or statement methods, there's about a 33% chance that you go away. Whereas if you put more than that down, there's only about a 5% chance that you go away. So we've just really improved the purity a lot by including that split. Well, what happens next? Well, we're going to try to split the left child. So it turns out that if we split on use, so if you're using the club, sorry, this is when you're not using the club. So if you put very little money down, you use one of these book and statement methods, and you're not using the club, notice the chance that you go away increases to 43%. If you are using the club, even though you put little down and you have one of these bad methods of payment, you see the chance that you go away is pretty small, only about 6%. All right, well, what does R do next? It says, can I split the left child further? And the answer is yes. So it's going to split on this categorical variable, send all the book people to the left node, all the statement people to the right. And so, let's just think about what this is actually saying. This is saying you're using book, you're not using the health club, and you put very little money down. There's about a 54% chance you go away. 0.54 is greater than 0.5, so it gets classified as a 1. What would R do next? Well, it would try to split that node. It can't do it, so it makes this a terminal node. It would then try to split the right child. So the right child would be those paying on statement. You see they're not quite as likely to go away. It can't split it, so that's another terminal node. It would go then try to split the right child if we go up a level in our tree, and you'll see that it can't find a good split, so it makes that a terminal node. What happens next? Well, keep going up the tree. Let's go try to split the right child. So the right child, remember, was when we had a down payment of more than $123. So it turns out that if you split it again with a larger down payment, $350, then if you put down $350, even though you have one of these bad payment methods, you're very, more than $350, you're very unlikely to go away, 0.001 chance that you go away. Whereas if you put down less than 350, but more than 123, then you're at like a 9% default rate. It tries to split this other node and it finds another split. So if you're not using the club, that's trouble. If you're using the club, even though you have one of these bad payment methods and you didn't put that much down, you're not that likely to go away. Okay, so I think this is a good example because it's found some interactions. So these are interactions because the effect of a payment method really depends on whether you're using the club and whether your down payment amount is large. So there's interactions between those variables, and our tree has discovered that for us. I think it also does a good job of illustrating for the first time how trees handle categorical variables. So it just pushes certain values like all the EFT methods to one node and the remaining values to the right. So trees are extremely good for handling categorical variables. If we had a variable like state, if we put that into a regression, think about what would happen. You'd introduce 49 dummies if you had 50 values of state, of the state of residence, that is. Whereas a tree would say, I'm going to go put certain states in the right child, other states in the left child, and I don't fragment my data too quickly. So that's a really important property to know about trees. I'll just mention one more thing. If I had some missing values, we could treat missing values as a categorical value. And maybe it pushes book statement or missing to the left, and it pushes EFT to the right. That would be another completely valid split for a tree. I want to just give you a little bit broader perspective on trees. So a couple terms. Regression trees have numerical dependent variables. Categorical variables are called classification trees. There's a lot of different trees that have been proposed over the years. I'm really focusing in on one method, which is CART. Another method that you should know about is C4.5. C4.5 is a method very much like CART, but there's a famous book that was written by the person who created C4.5 that describes a lot of the computational issues. So if you're interested in those computational issues in estimating trees, go read, go search that book. Another method that you should have heard of is called CHAID. So CHAID is called the chi-square automatic interaction detector. I'll give you a little bit of history on this. The first method was called AID, the automatic interaction detector, and that was proposed way back in the 1960s. I believe it was Morgan and Sonquist were the authors of that. Somewhere along the line, AID was expanded to CHAID, where they do a chi-square test on whether to introduce a split. CHAID is an extremely popular method in industry. So a lot of people will talk about CHAID trees, and that's the only method they've heard of. CHAID turns out to be not that great of a method for prediction accuracy. So it has a couple problems. Number one, it fragments the data too quickly because it doesn't restrict itself to binary splits. Number two is it's very conservative in the way it grows the tree. It only introduces a split if there's a significant difference in the proportions or in the means across the nodes, which means if there's a complicated interaction that maybe you don't see with the first split, then CHAID isn't going to find it. Whereas CART and C4.5 overgrow the tree and then they prune back. So that's a better strategy. So for those reasons, I would not use CHAID. I would stick with CART or C4.5. A couple other things. I mentioned that we always check stopping rules. Here are some common stopping rules. So if all observations are in the same class, there's no bother splitting it because you have a perfectly pure node. So stop. Stop growing the tree there. Another really commonly used stopping measure is the number of observations falls below some threshold, and in R that threshold is 10. So we're not going to introduce a split if we fall below 10 observations. Another stopping criteria is if the minimum change in deviance, so this would be a fraction of the root node deviance, falls below some threshold. So if you want to grow a big tree, set min-dev to a very small number like 0.000001, and you'll get a very big tree. Another method that's used in some other software packages is the tree depth, but it's not in R, and that's a good thing because again we're going to introduce a lot of binary splits. Maybe we want a very big tree to capture interactions. This is not a good stopping rule. All right, I want to do one more example with you and then wrap up this video. So this is an example that we looked at back when we discussed discriminant analysis. And the situation is we want to build a machine classifier so that we can make admissions decisions at our college. So let's say we have the grade point average of applicants and their GMAT scores. And we've had some human experts classify these applications into 3 groups. So deny, waitlist, and admit. And what we saw was that quadratic discriminant analysis did a little bit better than linear discriminant analysis and naive Bayes on this problem. But let's see how we do with trees. And it turns out trees are going to struggle a bit with this. And so here's the reason that they struggle. So I went off and I fitted a classification tree. This turns out to be the resulting tree. And so, we first split on grade point average of 2.7. So that's our first split. And we isolate a lot of the wait lists, but we got a few stragglers over here that didn't quite get captured. So what do we do next? We introduce another split on grade point average. What do we do next? Well, we make a split over here on GMAT score at 415. So 415 would be this value. And we do a bunch more splits. And so what I'd like to point out with this is tree methods are really struggling with this on this problem. The reason is this. Here's GPA. Here's GMAT. And the decision boundaries basically look like this. These are all denies. Then what happens is you're going to see there's kind of a hook right here where if you have a decent grade point average, we're going to waitlist you. And we're going to deny these people. Okay, so if you take tests very well, but you have a lousy grade point average, we're going to deny you. And then everybody over here is going to be an admit. Okay, so that would be the ideal set of decision boundaries, but what's happening is trees can't do decision boundaries that are not aligned with the coordinate axes. So trees search things like, where should I split GPA? Where should I split GMAT? They don't search some combination of these two. And so in order to capture a boundary like this, if I had a ton of data, what a tree would have to do would have to be to approximate that split with some series of step functions like this, and it would take me a ton of splits to capture that. So what do we do? Well, the answer is we could rotate our axes. So we're going to study a method when we get to unsupervised learning called principal components analysis. And I don't expect you to understand principal components analysis right now. We're going to come back to this a couple weeks. But what PCA basically does is it finds a rotation of our axes. So instead of having the GMAT and the GPA axes, we're going to do a rigid rotation. So what I mean is we're just going to rotate both of these axes a certain amount. So they maintain a 90-degree angle between them. And we have a new set of axes, these blue axes that are called the principal axes. So this is going to be the first principal axis. This will be the second principal axis. So instead of me using a tree method with the original coordinates expressed as the GPA and GMAT scores, what if I used the first two principal axes coordinates? These are called principal component scores. So these new coordinates with respect to the blue axes are called the principal component scores or principal components. So this is going to be the first principal component. This is the second principal component. I called it C1 and C2 for the coordinates. And what I want you to notice is we end up with basically what I had over here after I rotated my axes. So if your first principal component is less than some value, what that means is, well, deny them. If the first principal component is greater than some value, we admit. And then we need one more split, which is to separate, the people who can take tests well but can't study versus those who work hard and get decent grade point averages but don't do the test very well. We stick them on the wait list. All right, well, I want to illustrate one more thing with this. By default, the tree has given me some extra splits. So I don't think I need all these splits. I'm going to go prune my tree. So on this next page, I'm going to go use this, this prune function and say, just give me a tree with 4 nodes. And what you see is we end up with an amazingly simple model that is extremely easy to interpret. So it's this is something that you could turn over to any admissions officer, and they could easily execute on this. So if your first principal component score is greater than some value, you admit the student. If it's below some value, you deny. Looks like there's a problem with my font here, but that says deny. And then we have another decision point. Anybody in the middle, we have to go check that second principal component. If it's less than this value, you waitlist them. Otherwise, you deny them. And so I think this example illustrates the flexibility of a tree. It makes a very interpretable model that extremely simple to explain. This is way simpler to explain than what would come out of a discriminant analysis or what would come out of a logistic regression with multiple classes. Extremely simple to explain to normal people, and does a very good job of classifying that. I'm going to stop here, and we'll talk about this next one in the next video.